What the heck is up, guys? It's Jacob here, and in this video we're going to be taking a look at the silicon-controlled rectifier, or the Thyristor. Now, this component isn't really one of your most common electronic components. It's kind of more of one of those discrete components. It's not easy to find a ton of information on these, and they're not used very often. They're more used in higher power applications. They work very well in AC circuits. That's one very useful property of these, is they work in AC circuits. They are used a lot. Well, they're related to the triac, and the triac is more often used. You'll be familiar with the triac in like light dimmer circuits or phase control systems and AC systems, but the SCR is pretty much half of a triac. We'll take a look at a triac in another video. Before you watch this, make sure that you understand how diodes actually work, because an SCR is pretty much just a diode that's controlled with a gate. It's very similar to how a diode operates, which is why they work very well in AC circuits as well as DC circuits. So we'll look at some of the theory of operation behind these things, and I'll show you guys one set up here on an AC and a DC circuit, and we'll look at how it behaves. Alright guys, so I have here drawn the schematic symbol for the SCR, so it looks very much like a diode. And again, if you haven't watched my video on diodes, watch my video on diodes and I'll explain some of this in more detail. So we're not going to go into a ton of the nitty-gritty details behind these PN junctions, because a lot of it I already did in my diodes video, as well as my basic physics behind electricity part 5, where I talk about semiconductors. So we're not going to get incredibly detailed on this. I'm just going to kind of explain the operation of these PN junctions just at a higher level. We're not going to get all ridiculously advanced in this one. If you want to see what is actually going on, watch my diodes video. But essentially, this is just a diode with a gate, right? So that's what it looks like. So you have your anode over here. This is going to be, typically, if it's forward biased, your more positive terminal, right? And if it's forward biased, again, your cathode is over here, and it's going to be the negative terminal. And they're typically labeled A, K, and then your gate here is labeled G. And typically, you'll have your current flowing from your gate out to your cathode. These are current-controlled devices. They're not like MOSFETs, where you have a electric field control device. So they do require a little bit of gate current to actually flow through to activate this device. Alright, so here's basically what happens with an SCR. Here's the idea behind it. It's just like a diode, right? So it blocks reverse bias current. So current doesn't want to flow through here unless you go over the actual reverse voltage breakdown. So in normal operation, current flows the direction of the arrow, just like in a diode, alright? So it's just like a diode, but this component it has a forward blocking region as well, which we'll look at over here on the graph in a minute, but it has a forward blocking region. So this thing can act like a diode that is not on all the time, and you can turn it on, you can activate it, or put it in the on state, if you will, with this gate. And when you have a little bit of a current going through that gate, it'll actually activate this diode, or this SCR, right? So what happens is, once you activate it with this gate, current will begin to flow through to your load, right? And so what happens is this thing actually latches. So once you turn this SCR on, you cannot turn the SCR off until the amount of current flowing through from the anode to cathode is significantly small, below the holding current of this device. And you could find the holding current in the data sheet, but it's usually somewhere around tens of milliamps, depending on what kind of a component you're looking at. These come in all sizes, and these guys go up to hundreds of amps. We're talking large components. These are on like megawatt scale grid converters and stuff like that. So they are large components. And so they don't have like incredibly fast switching speeds or anything. They're not like MOSFETs or anything like that. So that's one downside to them, is they're not very fast switchers. So we don't use them typically as switches. Maybe just large power switches, but not high frequency switches or anything like that. So once you activate this guy and it turns on, it wants to latch there until the amount of current going through here falls below the holding current. Again, we'll look at that on the graph over here in a minute. So here's kind of what happens when this thing, I want to show you guys the actual PN junctions inside this guy. So under a normal forward biased operation, what's going to happen is your anode, of course, is going to be more positive, right? And your cathode is going to be more negative. And if we look at these two junctions right here, that's actually going to be forward biased right here at this junction right here, right? Because your P junction right here is more positive, right? And if you look at this guy, this is more negative, your cathode is more negative, and that's going to the N junction, so it's actually forward biased. So this right here, this junction is forward biased, this is forward biased, but so these really, this whole side here wants to conduct, and this junction wants to conduct when it's forward biased. But then if we look here, this guy is going to have a depletion region, right? Because if you look, it's going to be positive, positive, and current, this whole junction will conduct, and then it's going to hit right here, and this side is going to be more positive, and on the other side of this junction from the cathode, it's going to be more negative. And as you can see, there's a P junction, and if you watch my diode video, you'll understand this a little bit more. I'm assuming you kind of already know how a diode works and how PN junctions work. Watch my other videos if you don't, but I'll link those down below as well. But essentially what happens is this whole region is conducting, this is conducting, and once it hits this middle junction right here, there's a depletion region, and it does not want to conduct. So this is called the forward blocking state. We are forward biased, but it's still blocking. There's no current flowing. There's nothing. It doesn't want to conduct. It's not in the on state, right? And so when we apply a small positive voltage here at the gate, and a current flows through to our cathode, it actually removes this depletion region. So it does, this region here will become forward biased, and it too will become a conducting region as well. And what happens is this thing latches, and now current is allowed to conduct. It acts just like a forward biased diode, and current flows through. So even once you remove this voltage, let's just assume now you've turned the gate off and there's no voltage going to there. This actual SCR will continue. It'll latch. It'll turn into a latching state, and as long as you're above the actual latching current or holding current level, it'll continue to conduct until you fall below the holding current. And we'll look at the graph on that, like I said, but this guy will continue to conduct. They're not very easy to turn off unless the actual current flowing through falls below the holding current. There are other type of SCRs that are called GTOs, which you can actually apply a gate current which will actually turn the SCR off, but it requires a significant amount of gate current. We're not going to really look at that here. So if you guys watched my diode video, or if you know how diodes already work, you'll know that diodes work quite well in AC or DC circuits. If you have the diode forward biased and you apply a positive voltage over here, oh, well, that's what forward bias is, right? The current will flow in the direction of that arrow. And so if you apply an AC signal, you can also put AC power through this diode, and only your positive half of your waveforms make it through. This looks like a really poor wave, but you guys get the picture, right? Your bottom, your negative biased portions of that AC wave will not make it through. And you could also flip this, and the other half, it would be just opposite. You get your negative half of your sine wave, and the positive half would be chopped off. And so it does the same deal here. It behaves the exact same way, but we can get some very unique properties with this. One thing you guys might see is we can actually use this as a switch in an AC circuit. It can actually behave as a solid state switch in an AC circuit, kind of like a relay, and that's oftentimes what they're used for, because relays are mechanical components. They can fail, and they also have things like arc over, your contacts can weld, things like that. There's issues like that, so oftentimes you'll want to use a solid state component. But you can see an inherent problem with that is that only half of your actual sine wave makes it through, right? If we're talking 60 hertz grid, which is often what these things are used for, your half of your sine wave is going to make it through. So if you actually put two of these back to back, which we'll look at in another video, that's actually a whole other component called the triac, which has two of these guys hooked up, you can get the full half of your wave. But you can actually use it as half wave AC switching, right? So when you have this gate activated, it will allow half of your sine wave to make it through. If it's off, it pretty much cuts the power off. So it's a really good solid state switch for AC applications. Alright, real quick here, you guys can skip through this example if you want, because it's a little bit complex, and I'm not going to explain it in great depth here. We'll go into a whole other video on this, because this is an entire topic on its own. But it's such an important use of the SCR that I really have to cover in this. So just real quick, follow me for a minute. Here's an AC power supply, right? So this here is your, I really should have labeled this. This is your RL, or your load, right? It's a load resistance. Another thing I want to mention, SCRs don't do very well with inductive loads. We'll get into that in another video, but essentially you have a lot of power factor issues that come into play, and also your SCR could potentially kick in at the height, your peak of your sine wave in inductive loads, and that causes large surge currents and other issues like that. We'll look at that in another video, but right here I just want to talk about the SCR. I don't want to talk about really design issues with these SCRs, but essentially here's what's going on, right? So here's the AC circuit, and let's just pretend the SCR is not there. If it goes right through, right, your load is going to be powered from this AC sine wave, right? So when we put this SCR in here, basically it's going to allow current to flow on the positive half of this wave. So when this wave is positive up here, right, on the positive half of the cycle, current can flow through this SCR if it's enabled, okay? And so down here at the gate, we can actually latch this this SCR, right? I keep wanting to call it a diode because it looks like a diode, but it's not. It's an SCR. But anyways, so follow me here. If we have this, I put this little diode in here. This is just one of those jelly bean silicon diodes. It's just a regular silicon diode that you guys are familiar with, like a 1N4001 or whatever, right? And so what this is doing is just ensuring that we only have positive voltages going into our gate. We don't want negative voltages. It's not necessarily bad, but sometimes it can give us some issues with current flowing backwards through these junctions, which we don't want. So anyways, what happens here is when we have on the positive half of this sine wave, when this wave goes positive, first, if this gate is enabled, current will be allowed to flow through here, right, on the positive half of the sine wave. So if we drive the gate from this actual sine wave, this actual AC source, right, on the positive half of the wave, that voltage will flow through this resistor, or this variable resistor, right, and it will go through, and it goes through our diode and into our actual SCR, and it drives that gate. And remember, there is an actual amount of gate current that flows here. You're going to have a voltage drop from that, and you're going to have a voltage drop from the junctions inside here. But there is a gate current that you need, and that is that it's not really the latching current, but it's the actual gate current that you need. So we'll just call that IG, right? So the actual current that needs to flow through the gate of this SCR to latch it, to actually enable it, is IG, right? And so let's say, and we can determine how much current is going through this gate by using Ohm's law, right? It's V over R, so the voltage going through this over the actual resistance. What we can do is let's just say this resistor wasn't here and it was hooked straight up to the AC source. So what would happen is, if we're looking at this wave right here, the IG is actually rather small. It's not very much. It's just, you know, a couple tens of milliamps, and that'll be enough to actually latch this thing and turn it on to enable it. So it won't require very much voltage. And let's say right when the sine wave starts, right about here, that's enough voltage to actually latch this guy right here, right? So basically this thing's going to latch on and turn on throughout most of the sine wave, and it'll unlatch once we cross zero again. Once that current falls below the holding current, this thing will turn off. So our output waveform will start right above where that dot starts, and it'll look like that. So that'll be what comes out of, this will be the actual voltage that's flowing through this load, or the actual current flowing through the load, right? It'll look like this. And as soon as it hits zero, the SCR will cut out again, and you'll have to re-enable it. But what happens here is we can actually adjust this resistor to the point where it requires that AC wave to get a little bit higher, right? Because you're going to have a little bit more of a voltage drop across this resistor. So we can adjust this resistance so that it requires that wave to get a little bit more into the actual phase angle of that wave, right? So here we have 180 degrees, here's 90 degrees right here, and we can adjust what part of the actual AC sine wave where that voltage gets high enough to actually put enough current through this SCR to latch it. And that gets into what we call phase control. Again, I don't want to go into great depth here because that's not what we're talking about, but it's such a major use for these that I had to explain. And basically what it looks like, we'll actually look at that on the oscilloscope, I'll show it to you. But it basically allows us to, so on our output waveform of this SCR, if it was just fully latched, it would look like this, right? And you would have your positive half of your waves making it through as long as it was latched. Well, with this idea up here, what we can do is we can choose what part of the actual phase to start at, and let's say we wanted to start it right here, and we can cut off the rest of that phase, and it'll just jump up right there, and you'll only do half or whatever portion of the actual cycle you want to actually start at. And this can get into what we call phase control. This is how light dimmers work. This is how large motor controllers work for AC motors. So you can actually control it and limit the amount of power or the actual portion of the sine wave that makes it through to your load, all without ever getting into like DC, phase control or anything like that, because that's much more complicated. You have to get into there's a lot more circuitry involved in that. So this is very simple, and everything's done in AC, so we don't ever have to get into like DC motor controllers or anything like that. You can actually control loads directly in the AC domain without having to go into DC, which is really handy, and that's what SCRs, a big use of SCRs. And the triac kind of does the same thing. It's the same idea, but it'll actually give you the other half of your sine wave, and you can cut both halves of the actual waveform. And we'll look at triacs in another video. Alright guys, real quick before we actually look at some of these examples on the oscilloscope and I show you one of these guys in action, I just want to show you the IV curve for one of these guys. So if you look at it, it looks very similar kind of to a diode, right? Ignore all this. If you ignore all this and we just went straight through, this looks just like a diode, right? Just pretend it went and connected. It looks just like a diode. So it kind of has that diode characteristic to it, sort of, right? That looks like a diode. This looks like a diode. But here's what's going on. So we have three regions, right? So we have the reverse blocking region. This is the most obvious. I'll just say this first. So if it's reverse biased, it's going to work just like a diode. If you guys watch my diode video, you'll know if it's reverse bias, no current's going to flow through it because it's reverse bias until you hit the actual breakdown voltage, the reverse breakdown voltage. So this is called, I just labeled it VBR. It's called VBRR in some data sheets. Data sheets have all their own names for these things. It just depends on the manufacturer. They don't have really a good convention for it. So I just called it VBR. It's the reverse voltage breakdown. So if you go beyond this, the SCR will conduct, and that's usually not a good thing. You don't want to go to the actual reverse breakdown voltage. So anywhere in here, it'll be your reverse blocking region. This will be described in your data sheet. It'll say the maximum reverse blocking voltage and also the forward blocking region. So this you do not have in the diode, and this is what distinguishes this component from a diode. A diode doesn't really have a forward blocking region. It always conducts in the forward bias region, right? That's the point of a diode. But in this case, we can, if this thing is not latched, if we haven't enabled it through that gate, it will block in the forward region as well. And this is just small leakage current. That's what this is, leakage current. So it's not very large, maybe in the microamps or so, just depends, but not very large, not much current is all leaks through. And then basically you can hit, so this thing can actually enable in two ways. You can enable it through the gate, which is the most common practice, or if it hits the forward voltage, the forward breakover voltage, it will latch and turn on. So, but this is typically not used. You don't want to, when you're designing these, you don't really rely on the thing turning on from the forward breakover voltage. It can actually damage the component in some cases. They're not really designed for that. And in a lot of data sheets, they say not to even to go near the forward breakover voltage in your design. So typically these things are turned on from the actual gate, not the forward breakover voltage. But basically what happens is when this thing, so this region here is the forward blocking region, so current is not really going through, like I said, insignificant amount, especially for the power levels that these are typically used for. It's very insignificant. And then so what happens is you get to the actual latching current. So this is IL, this is the latching current. So if it's enabled, so it can either be enabled from the forward breakover voltage or from the gate, this thing will start and go into the conducting region. That's what we see here. So it'll pretty much instantaneously jump. That's what this is. It just jumps, boom, to the forward conducting region. So, and once you reach this latching current, this device will latch. That's IL. And IL and IH are typically the same or very close. They're really close within each other, but they're not always the same. So that you got to check that in the data sheet, but typically they're the same. And so this IL is the latching current. That's what's needed for this thing to stay on. If you're not within IL, if you're below IL, once your gate turns off, this guy will turn off. So that's what's needed for it to latch. And then once it's latched, again, it goes into that conducting state, and that's what you see up here. That's where it acts just like a typical diode, and it can conduct a lot of current. So this is so there's 3 states: the reverse blocking, forward blocking, and the conducting, where it just acts like a diode, right? And that's forward conducting, obviously. And so basically what happens is it'll conduct and it'll stay in this region until your gate is off and you have dropped below your holding current. So you have the current going through this SCR has to drop below the holding current. And if it doesn't drop below this holding current, it'll stay in this conducting region until both of those cases are true. Till the holding current, till your current drops below the holding current, and till your gate is turned off. Alright guys, so here is an NTE 5550, so this is a very old component, but this is an SCR. Again, these guys comes in all kinds of shapes and sizes. So this is just a TO220 package, but there are many other packages, and these guys come in very big sizes, because again, these things can control many kilowatts of power, and oftentimes that's what they're used for. And a lot of times, like I said, they're used for like solid state relays and things like that. So I have that circuit that I drew on the board earlier for that phase control. So it's hooked up. I'm not going to really show you guys the breadboard, because that's going to look, I mean, there it is. But you know, you're not going to really be able to follow that. It's what I drew on the board earlier, pretty much exactly. So we just have one of those little jelly bean diodes. Here is a 10K but little trimmer pot, and I think it's a 10K, maybe it's 100K. No, that's 10K. And here is a load resistor. So this is just a 100 ohm, 15 watt load resistor. So it's just a wire round resistor. And we're coming out of this transformer that puts out, I don't know, I want to say close to like 40 volts peak to peak or something like that. So we'll look at that on the oscilloscope. We'll see what it puts out, but I think it's 40 volts peak to peak. And this guy is a 50 volt SCR. So let's take a look at it on the oscilloscope, and I'll show you guys what I was talking about for that phase control. Alright guys, so I want to show you this on the oscilloscope. So here's the actual AC waveform coming out of the transformer, right? And then so if I flip this guy over, you can see both waves. So you can see that the actual output of the SCR through the load is chopped off. It's only giving that positive half of the cycle. So that's what the SCR looks like, just like the diode, right? So there's nothing fancy going on there. It looks just like we saw in the diode. So, but here's the cool thing. So when I turn this potentiometer, when I actually turn this trimmer pot here, you can see, I'll actually turn the other waveform off. You can see that we can start cutting off a portion of our actual cycle. So we can cut off part of our top half of our waveform, and this can be used as phase control. And so we can only, the way I have it set up, we can only cut off half the wave. I'll explain that in another video, but essentially we have to add some capacitors in there to do some phase shifting on our trigger line to actually get it to control the other half of our wave. So we can really only control a quarter of a full cycle with this right now, but that's what SCRs, that's a really good use of SCRs. They can be used to do what's called phase control. So that's actual AC phase control there, and that's how a lot of like light dimmers in houses work, and motor phase controls and things like that work.